Okay, welcome back for circles again. We're just not done with all of our circles. There's more to do with it. We've talked about all the parts of circles in the Circles 101. We talked about how segments get broken up by a circle in Circles 102. Now we're going to talk about angles within a circle. So this is our Circles 103. Circles 103, angles within a circle. We've already talked about one of these. We talked about the central angle of a circle being the exact same measure as its arc length, or the measure of the arc, sorry, not arc length, but the measure of the arc is the same as the measure of a central angle. So now let's talk about a certain type. Here when you look at this figure, you got to say, oh, hey, wait a minute, that angle, GFE, is not a central angle. How do we know that? Its vertex at that angle is not on the center of the circle. So what do we have to do with this? We got to give this a special name. We call this an inscribed angle. It's an angle formed by two chords or secants such that the vertex of the angle is on the circle. Notice point F is on the circle. Now, we made a conjecture about this angle from our circle activity, our circle investigation. And that conjecture was that the measure of this angle was equal to half the measure of the arc, or that the arc was half the measure of the angle here. So an inscribed angle formed by two circles, we got that. That conjecture we made is a theorem. We called it the inscribed angle theorem. And this is just the measure of an inscribed angle is equal to half the measure of the intercepted arc. So the measure of angle GFE is half the measure of arc GE. An inscribed angle yet here. There is the congruent inscribed angle theorem. And it says if two inscribed angles have the same arc, then they are congruent. And some of you found that out in the Cinder investigation. As you moved that point D around, the angles didn't matter. They always stayed the same value all the way around. And I say that's why you had to move point B or C. Because any two inscribed angles that have the same arc, they have to have the same measure. Now, we can go further with this and say we have the semicircle inscribed angle theorem. And it says if an inscribed angle intersects a semicircle, then the angle is a right angle. Why would that be? Well, a semicircle is 180 degrees. Half 180 degrees is 90 degrees. So if I intersect a semicircle, the angle, my inscribed angle, will always be a right angle. Now, other angles formed within a circle. There's several different types here. We have two secants can intersect in three different ways. Their vertex can be inside the circle, like here where point H is inside the circle. They could be on the circle, like what we just had, where F is on the circle. Or they could be outside the circle, here where point M is. M is outside the circle. We still have to be able to figure out what is the measure of each one of these angles. And this always comes back to the triangles, but we can simplify that process. Now, let's say angles can be formed by a secant or a chord and a tangent. If we do a secant and a chord, the angles can be formed by a secant and a tangent with the vertex outside the circle. But if it's a secant or a chord, a tangent, and either a secant or a chord, they always have to be on the circle. So when we bring in a tangent line, we have the option of either being on or outside. And then if I happen to have, again, we get the vertex on, we get the vertex inside the circle, but not necessarily at the center, and we get the vertex on, outside the circle. So those are all our options. So we got to figure out how to find the angles for that. So anytime we look at this type of situation, we're going to look at three different, where is the vertex of the angle? So if the vertex of the angle is on the circle, so that means I have a secant and a tangent, and the angle is formed on that. So that could either be my secant GE and my tangent ME, or my other secant and my tangent. Or if I have two secants whose angle is on the circle. Okay, anytime it's on the circle, think of it as an inscribed angle. And if it's an inscribed angle, that must mean that the measure of the angle is half the arc. If two segments, excuse me, If two segments intersect in such that the vertex of the angle is on the circle, then the measure of the angle is equal to half the measure of the arc. So anytime that vertex is on the circle, the measure of the angle, it's half the measure of the intercepted arc. That's the arc inside the angle. Now here's what I want to point out to you. You have to look very carefully about where the inside of that angle is. So let's say here was my tangent line, and here was my secant line that happened to intersect. The angle inside this arc is this angle right here. That's the angle that I'll have to take half of. Now, what if it wasn't that particular set? Hope these things disappear. Oh, let's change my color. Let's go to yellow. Let's shorten it up a little bit. Okay, let's say it was this secant line and this secant line. And I'm looking for its intercepted arc. That's the arc inside the angle. The intercepted arc will always be the one inside the angle. Let's try a different kind altogether. Let's try, say we had, again, this tangent and this tangent, but I knew this arc here. Okay. Oops. I knew this arc over here. I won't make the circle on it. Okay? It's whatever arc is inside the angle. And that's the thing we got to watch for, is which arc is inside. So, our secant tangent angle theorem, our secant angle theorem, if you look in your book, this is from chapter 9 in your book, these two theorems are written as if two secant segments or if a secant and a tangent did intersecting on the circle. I combined them into this one theorem. If it intersects on the circle, it's half the measure of the arc. That's the thing I want you to get from this. Now, what if the vertex is inside the circle and it's not at the center? If it's at the center, we know that the arc is equal to the angle, and the angle is equal to the arc. But what if I have an intersection like here, where point M is not at the center of my circle? How do I find the measure of the arc? How do I find the measure of the angle? The theorem says if two segments intersect inside the circle, not at the center, then the measure of the angle formed is half the sum of the angles of the arc in its vertical angles arc. Okay. So we're good to go here. So here is the angle I want to find the measure of. Okay, let's say that's the angle I'm doing. So its arc is this side right here. Right on the money, right? Okay. Which one is its vertical angle? Its vertical angle is this one over here. So its vertical angle's arc is this one here. So I would take this larger arc here on the left and the smaller one here on the right. I would add those together and then take half of that. Half of the sum of the measures of the arcs. Why half? Well, I have two angles that are being formed by these two arcs, so I have to find their average to get it. Okay, so there's that. So if we intersect on the circle, we're doing half the measure of the intercepted arc. If we intersect inside the circle but not at the center, we're going to take two arcs, add them together, and then divide by 2. Now, what if our other situation that we had? Remember, we had 3 situations. We had on, inside, or outside the circle. So here I actually have 3 different scenarios that could happen. I could have 2 tangents that intersect. I can have a secant and a tangent that intersect. I can have a secant and a secant that intersect. And all of them have the vertex of the angle outside the circle. So again, if you looked in your book, they give you 3 different theorems for this. I'm going to condense it all down into one, and I'm going to say if the vertex is outside the circle. So I got 2 segments that intersect outside the circle. So then the measure of the angle that we have is half the difference of the larger arc minus the smaller arc. Got that? The measure of the angle is half the larger arc minus the smaller arc. Again, notice that half is in there. Anytime the angle vertex is not at the center of the angle, or not at the center of the circle, we're going to do half. If it's outside, we're subtracting. If it's inside, we're adding. So here we have it outside. So here it says, okay, I have the angle of this arc. Let's go back to our yellow. Here's my angle that I'm looking at right there. Notice I get two arcs that are formed. I get this larger arc, and I get this smaller arc. Let me change that to a different color so we can see that better. Here's my smaller arc right here. Got the larger arc in yellow, got the smaller arc in red. So what I do to find the measure of my angle out here at M is I take KGF minus LF. KGF minus LF, arc, measure, and then I divide that by 2. That's what we want to do with this particular situation. Okay, so now we've talked about all the angles that are formed in a circle. If I have an angle where the vertex is at the center, I know the angle and the arc have the same measure. If I have an angle that is formed by two chords or two segments intersecting inside the circle, I know I have to find the two arcs, add them together, and divide by 2. If I happen to be right on the circle, I figure out which arc it is, and I take half of that angle. And if it's outside the circle, all I'm going to do is take the bigger arc minus the smaller arc and divide it by 2. So this ends Circles 103.